Swayam Prabha. Digital India. Educated India.
So the topic of this lecture is fluid mechanics of packet column. So as you may recall, a packet column is something that is used for mass transfer operation. So this basically consists of a cylindrical column with packing material to facilitate gas liquid contact. Gas goes in from the bottom, leaves at the top, whereas liquid enters from the top and then leaves at the bottom. So there are two fluids, two immiscible fluids that are flowing countercurrently in a packet bed. Okay. So we would like to basically, the scope of this topic is to calculate the pressure drop associated with this particular packet column. The scope is to calculate pressure drop as a function of gas and liquid flow rates. Now, once we know this pressure drop for this particular packet column, we can use to calculate the desired diameter, okay, for the packet column. Okay, so ultimately we want to calculate desired diameter . So before we look at the pressure drop calculation for a packet bed where there are two fluids flowing in countercurrent fashion, and then using the pressure drop to calculate the diameter of the column, we will first recall some of the known results from fluid mechanics. Okay, for example, think about consider a laminar flow through a circular hollow tube. Okay, so here we are thinking about a hollow tube or pipe, and a single fluid is flowing through it in a laminar flow. So if there is a laminar flow, we know the velocity profile. This will be parabolic, reaching maximum velocity at the center point and then 0 at the boundaries. So if you have a Newtonian fluid flowing in a laminar condition in a circular pipe, we know how to calculate delta P, the pressure drop, using Hagen-Poiseuille flow or Hagen-Poiseuille equation. So generally this is pronounced as Hagen-Poiseuille, but the actual pronunciation should be just Poiseuille. The LLE is actually silent. It's a Poiseuille. Okay, so it's something like Poiseuille. Okay, this is a pronunciation guide. Hagen-Poiseuille. Okay, Poiseuille. Okay, so apparently we don't have a French student here who can help us get through this pronunciation. But so Hagen-Poiseuille equation is used for calculating pressure drop for such as simple situations. Okay, so in this case the pressure drop is written as something like F is equal to 16 by RE, where the Reynolds number has to be smaller than or equal to 2100. Okay, this F here is the fanning friction factor, and this is defined as delta P by L like this. Okay, where D is the diameter of the tube or diameter of the pipe, rho is the density of the fluid, L is the length of the tube, so this is L and this is D, and V, so V, as I said, has a profile, but here the V is the average velocity. Okay, basically it's radially averaged velocity, and delta P is the pressure drop, basically P2 minus P1. So P2 is the pressure at the outgoing fluid and P1 is the pressure at the incoming fluid. So that is the difference we are talking about. And Re here is the Reynolds number defined based on the fluid properties. So now we can substitute this for F and Reynolds number. So you'll get so this is the equations that we can calculate the pressure drop for a laminar flow through a circular tube of a Newtonian fluid. So either you must have studied in this particular friction factor formula or in terms of explicit expression for delta P. Okay, either way. Okay, so clearly this equation is a very nice equation, very useful, because it tells you quantitatively how the delta P pressure drop will vary if you change the length of the tube or the fluid properties like viscosity and the flow rate, in this case velocity. You might recall when I was talking about absorption, in the choice of the solvent, we said the solvent should have smaller viscosity, lower viscosity. Okay, the reason is here. Okay, as you can see, the delta P is proportional to viscosity. If you have a liquid or a fluid with higher viscosity, it's going to add up more pressure drop. So given a choice, you should be able to make a lower viscous fluid. Okay, that's because it's connected to the delta P pressure. Interestingly, you can also see this delta P is also proportional to 1 by d square or 1 by area. Okay, so if I double the diameter of the pipe for the same flow rate, same velocity here, you will see that the delta P goes 4 times less. Okay, because of 1 by d square dependence. So this is a very important aspect, because this is what we are going to use in the further discussion, where having known the delta P, we can identify what should be the corresponding diameter. Okay, so the relationship between the required diameter and the target pressure drop is related to these kind of equations. But this is only applicable for a very simple flow through a hollow tube, laminar flow, Newtonian fluid. Okay, but we have much more complicated situation than this. So moving forward, the next sophistication we can add to this is flow through a faggot bed. So we have a cylindrical tube like before, but instead of this being hollow, we have a packing. So this can be packed with the different kinds of material. For example, you can actually pack them with same sized solid particles, and or you can actually use the packing material that I discussed for absorption problems, like rashing ring, interlock saddles, and so many packing material I had discussed in one of the classes. So the packing can be made any of those material. Okay, the idea is that this packing will allow a good interfacial contact between the two immiscible fluid systems. Okay, so that's why this packing is important. Now let's think about a packing is made, and then let's say one single fluid is flowing in. So fluid in and fluid out. Now, because of the fact that there is a packing, the fluid does not flow like the way it flows in a hollow tube, because in a hollow tube the entire volume is accessible for the gas flow or the fluid flow. But in the case of packing, you will see that there is a tortuous path through the packing that the fluid will have to move through. Okay, so if you have to just draw a small micro picture here, you might see some solid particle closely spaced, and then this through this porous gap the fluid will have to move through, right? So the available volume for the fluid to flow through is now very less compared to a hollow tube. So because of this effect, the pressure drop for a fluid going in and going out will not be exactly the same as the pressure drop that we get from Hagen-Poiseuille equation. Okay, so we need a little bit more a better formula or a method to calculate pressure drop for a fluid flowing through a packet bed. Okay, we are talking about a single fluid right now, and this is obtained through what is known as this Ergun equation. So this is a very famous equation, and so Ergun equation basically kind of is a synthesis of pressure drop expression from various other models. Okay, it goes something like this: Fp is equal to 150 divided by N Rep plus 1.75. If you look at this, it has a similar kind of functional form like the Hagen-Poiseuille equation. Okay, so there we had F is equal to 16 by NRE or x 16 by Re, which is a theoretical result. You can derive it. Okay, so inspired by that formula, the Ergun equation is actually written in a very similar kind of formula. Okay, so you have an additional constant here, and then you have this inverse dependence on the Reynolds number. Okay, and the prefactor is also there. Okay, so now this Fp here is the fanning friction factor for a packet bed. Okay, this is defined differently than the fanning friction factor that we saw in the previous model. And similarly, this Rep is the Reynolds number. This is defined for a packet bed. This Fp here is defined as like before with the additional terms. So you can see this Fp has additional terms. In this case, this epsilon here is the void fraction. Like I said before, the column is now packed with some solid material, and the amount of empty space available is now reduced. Okay, so this epsilon here is the fraction of volume available for the fluid to flow through. So it's basically a void fraction or the porosity. Okay, and this is the only available volume for the gas to flow or the fluid to flow. Other terms in these equations are same as before. Okay, I might say that this particular d, we will put dp here, and dp is not the diameter of the pipe, it is actually diameter of the packing material. Okay, Let's say if I have a spherical particle used in the packing, dP would be the diameter of the packed material. Suppose if the packing material is not spheres, let's say they are actually in some odd shaped packing material, then what we do, we actually calculate volume equivalent diameter of the particle. Okay, so we equate the volume of the actual packing material to an equivalent spherical particle, equate the volumes, and then get the diameter of the equivalent sphere. Okay, so that's the difference. So in the friction factor defined for packed bed, the only difference is how we deal with this diameter and then introducing this additional terms involving the void fractions. And Reynolds number is also slightly differently defined. This is defined with respect to, again, the characteristic of the packing material, packed bed's porosity. Okay, and here also the same dP is used, the same length scale is used, and V here or V there, okay, both of them are same. This is basically it's called the superficial velocity. So that means when if you measure the velocity of the fluid before it enters the packing, okay, or in other words, if the fluid were to flow in a non-packed hollow tube, what would be the velocity of the fluid? That's the velocity should be used here. Okay, so those are some of the corrections we have to keep in mind. Sorry. So what I'm saying is this velocity here is related to the superficial velocity, which means if I send the same fluid in the absence of a packing, the corresponding velocity should be used here in the entrance. Entrance or exit doesn't matter, because if you have a hollow tube, the velocity will be constant from the bottom to top. Okay, so you can use the velocity at the entrance. Okay, so superficial velocity at the entrance. So let's substitute all these terms here. So this is the full form of Ergun equation. If you think about why there are two terms, actually this is a more comprehensive model. This actually can handle flow in the laminar condition as well as in the turbulent condition. So this particular term is used when the flow is predominantly laminar, and this term is used when the flow is turbulent. Okay, so Ergun equation is actually used for both cases. Now, if you look at this Ergun equation, it's quite complicated. You see that there are properties of the fluid enter into this equation, the property of the packing is entering into this equation, and also the operating conditions. Okay, so what are the operating conditions? Operating conditions such as velocity, delta P, these are all operating variables. And then you have the nature of the packing enters through this porosity epsilon and dP. Okay, so these are all packing material based quantities. And quantities like viscosity, density, these are all related to fluid properties. And then geometric properties like L and D. So these are all geometric properties. So that means this equation can actually take care of flow of different kinds of fluids, different kinds of packings, and different kinds of operating conditions. So in the case of Hagen-Poiseuille equation, I showed that delta P is proportional to 1 by d square or 1 by area. Okay, but that is for a hollow tube. And we can see a similar, we can also find some similar dependence or equivalent dependence in this particular Hagen equations also. Okay, let's see, we wanted to, I want to introduce a new variable here. Let's say this velocity that we have here, V, I said this is superficial velocity. Okay, this is a velocity of the fluid when there is no packing. Okay, and this is related to the volumetric flow rate divided by area, right? Q by A. Q is the volumetric flow rate, A is the cross sectional area of the packed bed. And I can write this volumetric flow rate as mass flow rate divided by density times A, right? Now I want to give a new variable called G. This is called the mass velocity or the fluid mass velocity, defined as m by A. Okay, so this will have the units of kg per meter square second. Okay, so why we write in terms of per unit area, the flow rate per unit area is basically the mass velocity, is because we know that in mass transfer we write in terms of flux quantities. Okay, how many moles per unit area the mass is transferred. So we want to have some sort of similar treatment for the flow rate. So instead of volumetric flow rate or mass flow rate, we would write mass flow rate per unit area. Okay, so that is called the fluid mass velocity or mass flux. Okay, so that means I can now replace this m by A as G. So I have G by rho. So the velocity, the superficial velocity, is essentially related to the mass velocity divided by density, right? So now let us go back to this Ergun equation and replace this velocity here and here, because only those two are the terms involving the superficial velocity, and write this in terms of the mass velocity. So I can replace this Ergun equation velocity with respect to the gas or the fluid mass velocity. Okay, so you can see now I have got G square term here, G here. Wherever I had velocity V, I have written this in terms of fluid mass velocity. Okay, if you have turbulent flow, I mean generally the packed bed operates under turbulent conditions, so that means we have to worry about this particular term. So then I can show this delta P by L is actually proportional to g square, isn't it, in turbulent conditions. So delta P by L, that is the pressure drop per unit length or pressure drop, is proportional to the square of the mass velocity. Okay. So what does this mean? So that means delta P is proportional to, what is G? G is nothing but m by A. So if I have a fixed mass flow rate, right, I can change the area and then control the pressure drop. That's what this means. So delta P here is proportional to 1 by A squared. Okay. In other words, this is proportional to 1 by D power 4. Right. So if I increase the diameter of the column twofold, the pressure drop will actually decrease 16-fold, D power 4. So you can see the consequence of how pressure drop and the diameter of the columns are actually related because of this pressure drop calculations. Okay. Yet again, we are not talking about the complete problem yet. We are still talking about a packet bed with a single fluid flowing in, for which we have an analytical expression, and then we can see the dependence of delta pressure to the area or the diameter of the column. Okay. But the key is here that what is the dependence of delta P with respect to diameter and how we should work with it. Okay. So this is very important. We'll keep we'll come back to this again, even though this is not the full problem in hand, but we can see delta P is a very strong function of the area or the diameter. Okay, and they're actually inversely proportional to some powers. So now we'll focus our attention to the flow of fluid mechanics. Of packet column. Okay, this is our original problem. Okay, so here we have a packing. So here gas goes in, gas goes out here. Liquid comes in and then goes out here. So here the flow is a little bit more complicated, right? Because when there is only single fluid was going, the single fluid was actually going through the porous volume available in the packed material. Okay, but in this case, when there are two fluids flowing countercurrently, and if I have to kind of take a small area, small region here, and if I just try to zoom in here, you will see there will be, let's say there are packing materials. Okay, so here I am showing the packing material as some spheres, but it can be any other packing material. So here the gas will try to find the porous path to go in, and the liquid will find the same pore volume to go out. Okay, so because of this intricate porous path, there is a good interfacial contact between the gas and liquid. This is what we want, but as a side effect, as a consequence, we also have to face the pressure drop issues here. So that for the same porous volume, two fluids are going in countercurrent fashion. Okay, so now we want to ask, what is the pressure drop for the two fluids, as I set certain flow rates for both fluids. Okay, in the case of the Ergun equation with a single fluid, it depends only on the mass velocity of single fluid. But here in the packet bed with the two fluids going countercurrently, the pressure drop will depend on both of the fluids' mass velocities. Obviously, because both of them are actually affecting each other in terms of the path available for flow. Okay. So apparently there is no nice analytical equation to calculate pressure drop for these situations. So generally what we have is, we have experimental data presented in a tabular form or in a graphical solution. So we don't have an analytical solution because the problem is too complicated. Okay. So, so what we see here is a characteristic of pressure drop plots. Okay, for packet column with the two fluids flowing. On the x-axis we have gas flow rate. On the y-axis we have delta P. This is G denoting the gas flow rate. Delta P here is the pressure drop. Okay. So first thing you will notice here is that the pressure drop will increase with respect to gas flow rate when you have a dry packing. So what is dry packing? Suppose if only one fluid is flowing, no liquid is flowing in. Let's say only the gas is flowing from the bottom to the top. Okay, so that is basically corresponding to Ergens equation situation. One fluid only one fluid is flowing in, and then you have this dotted line here. This corresponds to the dry packing. Only one fluid is flowing in, only the gas is flowing in, no liquid is flowing in. In that case, delta P versus G, we know what formula to use. It's a Ergens equation, and we already saw this. In this case, delta P is proportional to G squared. So the slope here will be 2. Okay, so that's one of the limiting conditions. Okay, now let's say you start turning the liquid in. Okay, when you start the liquid in from the top, so the liquid will flow through this porous path, and it will limit the available volume for the gas to flow in. Okay, so this will definitely lead to increase in the pressure drop. Okay, so if I look at the same gas flow rate, if I go to some small, the line that you see here, the line AB, that is corresponding to a fixed flow rate of liquid. Okay, so the flow rate of liquid is fixed at some very small value, and then you increase the gas flow rate. In this case, like before, like in the case of dry packing, the pressure drop will increase, but it will be little more than the dry packing because the liquid will also occupy the same space. Now, if you keep on increasing the liquid flow rate, so here the middle can be the flow rate of liquid of a moderate flow rate, or you can have go to a very high liquid flow rates. Okay, so for a given gas flow rate, as you increase the liquid flow rate, the pressure drop will increase. Conversely, if I keep the flow rate of liquid constant, if I increase the flow rate of gas, pressure drop will increase. Okay, that's what these plots mean. But this dependence of slope 2 or about 2 will not be there all the time. This is only valid when the gas flow rate is moderate. When the gas velocity or when the gas flow rate actually increases higher and higher, what will happen is it will try to resist the downward flow of liquid. Okay, it will try to balance the gravitational force acting on the liquid. The liquid is only coming down because of gravitational force, but if the incoming gas is flowing so high speed, it can actually support the liquid in the column and not allow them to come down. Okay, then the liquid hold up in the column will start increasing. Okay, so this is called loading of the liquid, or the liquid is getting accumulated in the column. When this happens, then the lot of this pore available for the gas flow will be now filled with the liquids. Okay, so then you will see the slope of this line will start increasing from the slope of 2. Okay, so when you see a upturn in the delta P as you increase the pressure drop, it's an indication that the liquid volume fraction is keep increasing because the gas is not allowing the liquid to come down. Okay, it is loading the column with the liquid. This is called loading or loading zone. This will happen at all liquid flow rates. Okay, so if you compare between point B and B prime, you can see that when you increase the liquid flow rate, the loading will start at even lower gas flow rate. Okay, so if you compare the flow rate of gas at B prime and B, you will see that at a higher liquid flow rate, the loading starts at lower gas flow rate itself, whereas when you go to lower and lower liquid flow rate, the loading will start at higher gas flow rate. Okay, and it's also very intuitive. When the more liquid is coming in, at a very low flow rate of gas itself, the liquid will start getting accumulated. So this line B and B prime, that's where the loading starts. okay. But this loading cannot only keep on happening. At some point of time, this entire column will be filled with liquid. All the pores are now filled with liquid, okay. Now where will the gas flow in through? The gas will have to bubble through the liquid, okay. So that is called flooding, and the flooding starts here. And in this case, the pressure drop will actually shoot up very much, as if the column is actually unstable, because initially you have two-phase flow. Now you got phase inversion. The column is filled with liquid and the gas is now bubbling through it. It becomes more like a bubbly flow. So this is called phase inversion, okay. So when this happens, the column will have a very huge pressure drop, okay, shown by this, okay. So the important thing to remember is there is a flooding zone and there is a loading zone, and there is this operation where the column can operate safely, okay. So if I have to show this maybe pictorially, so when you have loading zone, you have this packing material here. So liquid is supposed to flow through here, and then gas supposed to flow upward, and then the more liquid will actually start accumulating in this pore. When you go to flooding situation, it will be like the entire pore will be filled with liquids, okay. All this pore will be filled with the liquid film, and the incoming gas will have to bubble through, okay. It will go as bubbles, okay. Do you follow the loading and the flooding? So let's just summarize what we have done here so far. So we are basically interested in the pressure drop calculation for a packed bed in which two fluids are flowing in. So before we did that, we looked at calculation of delta P for a single fluid flowing through a hollow tube under laminar condition, and this is very well studied through this Hagen-Poiseuille equation, okay. And we know how delta P will depend on the diameter or area of the pipe. Then we moved on to a more complicated situation where the tube is not hollow, but it is packed with a bed of materials, okay, packed materials. In this case, the pressure drop is given by Ergen equation, which handles both laminar as well as turbulent conditions, and we have to define the fanning friction factor and a Reynolds number accounting for the porosity of the bed. So we introduce this porosity as an additional variable in this problem. And then we showed that if you look at turbulent flow conditions for a single fluid flowing through a packed bed, the delta P will be proportional to the square of the gas mass velocity, okay, or gas mass flux, or in other words, this would be proportional to 1 by area squared or 1 by d power 4, okay. Now further we moved on to packed column in which there are two fluids flowing countercurrently. In this case, there is no standard set of equations to study pressure drop, because a pressure drop will be a complicated functions of flow rates of both fluids as well as porosity, fluid properties, the viscosity and density of both fluids, and the properties of the packing and so on. So, okay. So now the problem is so complicated. We have only experimental data available in terms of these forms, okay, where delta P is measured in terms of gas flow rate for a fixed liquid flow rate. And when you do this over a very large variety of flow rates and different kinds of packing, some generic feature emerges. The generic features are that when the flow rates of gas and liquid are very small, the pressure drop will increase with both flow rates. With the gas flow rate, it will be close to G squared, but with the liquid flow rate, it is not very apparent here because it depends on a lot of factors. But you can see qualitatively that as I increase the liquid flow rate for a fixed gas flow rate, the pressure drop will increase, okay. But when you go to very high flow rates of gas, you will see that it will affect the flow of the downcoming liquid, and then it will make the liquid accumulate in the column, which we call this as a loading, okay. Liquid accumulation is called loading point, okay, where the volume fraction or the hold up of the liquid keeps increasing. And if you keep on pushing the flow rate even beyond, then the entire column will be filled with the liquid, okay, and the gas will have to go through bubbles. They have to go as bubbles through the column of liquid, and that we call as a flooding. Flooding is a place where you don't want to operate the column. Okay, it's very unstable and the pressure drop is huge. So flooding is the maximum point up to which you can operate the column. So you have to choose your diameter of the column and gas liquid flow rates such a way that you are always below the flooding point. Okay, so that's very important, and in the subsequent class I will show how this pressure drop curves are plotted, okay, and how we can use those information to calculate the pressure drop as well as to decide what should be the diameter of the packing column. All right, yeah, okay, so we'll kind of stop here.